Welcome back. In this video, we're going to do 7.1.4, definition 7.1.4 on expected value, and theorem 7.1.2 on the law of the unconscious statistician, or LOTUS. Definition 7.1.4 says the expected value of a random variable x is e of x. That is the sum, we're talking about if x is discrete here, of all little x values in the support of x. Right, so that is all little x values that big X, the random variable, can take, of x times p sub x of x. If x is discrete, then this is our probability mass function p sub x of little x. If x is continuous, then we have to calculate the expected value as an integral. It's an integral from minus infinity to infinity of x times f sub x of x dx, where f sub big X of little x is the probability density function. The expected value of x corresponds to our intuitive notion of average or mean. And so very often we will write mu or mu sub x for the expected value of x. Theorem 7.1.2, the law of the unconscious statistician, LOTUS. If x is a continuous random variable with probability density function f sub x of x, and if t is g of x, so a function of x, then the expected value of t, which is the expected value of g of x, is the integral from minus infinity to infinity of g of x, which is t, times f sub x of x dx, provided that this integral converges. A couple of things to point out here. If x is a random variable, that means x's values depend on chance. So if t depends on x, and x depends on chance, then t also depends on chance, which means that t is also a random variable. If t is a random variable, if it's a continuous random variable, it also has an associated density or mass function. To calculate the probabilities for t would require knowing its, well, if it's continuous, its density function. In other words, knowing the distribution of t. LOTUS, this theorem, does not give us any information about the distribution of t. It only tells us about the average, the mean, the expected value. Those three words mean the same thing. Nothing more. The name of the theorem is said to come from those who use it without realizing what a remarkable result it is. You're using the distribution of x to get information about t. In particular, one might be tempted to think that if t of 1 is g of x1, and t sub 2 is g of x2, then you could calculate the probabilities of t by using probabilities of x. While tempting, this is very wrong. So this theorem, this LOTUS, tells us that we can use x, the distribution of x, to get some information. We can get the mean or the expected value of a transformed value t, of a function of x, but nothing more. In the next video, we're going to go and see an application of this function, which is going to be on linearity and helping us define what variance of a random variable is. See you then.